this lesson is 3.3 of the textbook. It is derivative of trigonometric functions. That's what we're going to study in this lesson. Well, I'm going to give you guys several formulas that I think you guys should just need to remember to be able to do homework. Then I'll show some of the examples, and then we'll work more examples in class. So here's the theorem. The first two formulas are derivative of sine, which is cosine of x, and derivative of cosine of x, which is negative sine of x. Then we have derivative of tangent equals to secant squared, and derivative of cotangent is negative cosecant squared. Then we have derivative of secant, which is tangent x sine x, and derivative of cosecant is negative cotangent x cosine x. So these are the 6 formulas for trigonometric functions that we're going to use a lot throughout the course of this semester. In remembering these formulas, it's easy to remember that the negative sign goes to the co-function. As you can see, cosine goes to negative sine, cotangent goes to negative cosecant squared, and then cosecant goes to negative cotangent cosecant. Well, here are some trig identities that will be useful when you do homework for this section. And these identities are, should be covered in trigonometry. Well, we have these formulas to relate basic trig functions with each other. So we have tangent of x equals sine of x over cosine. We have cotangent of x equals cosine of x over sine of x. Then we also have secant of x equals 1 over cosine, and cosecant equals 1 over sine. So these 4 formulas are those that relate trig functions with each other. And then we have the following identities. Sine squared plus cosine squared equals 1, tangent squared plus 1 equals secant squared, and cotangent squared plus 1 is equal to cosecant squared. And here are the examples. Let's say we want to compute the derivative of x cosine of x. And as you can see, it is a product of 2 functions. So we have x multiplied with cosine x. We will need to use product rule, which if we write it out, it looks like derivative of x times cosine plus x times derivative of cosine. Then, as you can see, derivative of x is 1, so we have just cosine, where derivative of cosine is negative sine of x, in which we use the formulas that are that is highlighted, as you can see over there. Okay, so again, derivative of cosine of x is negative sine of x, and then we can rewrite the formula as cosine of x minus x sine of x. And that's how we use product rule together with derivative or trig functions for this example. Next one, tangent of x over x derivative. Well, we have a quotient here, so we're going to use quotient rule. And if we write the quotient rule out, we'll have something like this, where x squared is in the denominator. The numerator is tangent of x prime times x minus tangent times x prime. And we're going to use the formula to take the derivative of tangent. And derivative of tangent is secant squared. Therefore, we get that formula. And then the next example is sine squared of x. And this is a little bit more tricky. Well, later on we will learn chain rule, which is another way to compute this derivative. But with what we have known so far, we can also compute the derivative of this, because sine squared can be written as sine of x times sine of x, and then we can use product rule again, because we have 2 functions multiplied to each other. So if we write product rule out, and then we have sine prim times sine plus sine times sine prim, as the product rule said, and we already know sine of x, derivative of sine of x is cosine of x. Therefore, we'll have the final answer to be 2 cosine of x, sine of x. And the last example is derivative of tangent of x. So in a way, we are proving the third formula in the theorem on the left. Well, we can write tangent of x as sine of x over cosine of x. So when you take the derivative, we're going to use quotient rule because we have sine of x over cosine of x. And quotient rule is saying that the derivative is sine x prime times cosine minus sine times cosine prime over cosine of x squared. And we're going to use derivative of sine of x, which is cosine of x, and then derivative of cosine of x, which is negative sine of x. And that's why we get this. The bottom, which is cosine of x squared, is kept the same. It doesn't change. Okay. Now, we have cosine of x times cosine of x. That becomes cosine squared. And then negative sine of x times negative sine of x becomes plus sine squared. Guess what cosine squared plus sine squared is? As you can see in the identities for trig functions, it is equals 1. Therefore, the whole answer is going to be 1 over cosine squared, which is nothing but secant squared. In this section, we will also use the following theorem, which says the limit when x approaches 0 of sine of x over x equals 1. We can prove this theorem using trigonometry, but we will not cover it here. You can read the proof from the book, or of course you can always ask me. How can we use this theorem? We use this theorem to prove or to compute the limits, just like in these examples. Let's start with limit when x approaches 0 of x over sine of x. Well, we can write x over sine of x as 1 over sine of x over x. And we know the limit of sine of x over x is 1, so the denominator goes to 1. Therefore, the limit is 1. So example B is the limit when x approaches 0 of sine of x over 3x. Sine of x over 2x. It doesn't look exactly like sine of x over x, but we can make it look like sine of x over x, because if you notice, we can pull the 2 in the denominator out in front of the limit as a 1/2, and then we have limit of sine of x over x. And we know that limit is 1, so the limit is 1/2. For example C, we have limit of x approaches 0 of sine of 2x over x. Now we don't really have sine of x over x, but we have sine of 2x over x. And notice that we cannot pull the 2 out in front because sine of 2x is not 2 sine of x. So what should we do with this? Well, what we can do is we have sine of 2x. So we want to have a 2x in the denominator so that 2x in the sine and 2x in the denominator look like the same. How can we do that? We can multiply 2 to both top and bottom. There you go. We have sine of 2x, and then we have over 2x in the denominator. And with this 2, with this number 2 right there, we can actually pull it out in front, and then we're left with the limit of sine of 2x over 2x. And that limit is also 1. Okay, because we have 2x in the argument of sine to be the same as the one in the denominator. So the whole limit is 1. Now let's check this example, where we have limit of 4x over sine of 3x, where x approaches 0. We're going to do something similar to C, but let's pull this 4 out first. Okay, so when we pull the 4 out, we get 4 times limit when x approaches 0 of x over sine of 3x. Guess what? We have something very similar to c, right? We have sine of 3x, but we don't have 3 for the x in the denominator, numerator. So what can we do? We multiply 3 to both top and bottom, so that we have a 3x to match with the argument of sine. And just like before, we can pull this 3 out in front of the limit, which looks like 4 over 3 because 3 is in the denominator. And then the limit becomes limit of 3x over sine of 3x. And that limit looks just like the one in example A, which comes out to be also 1. Therefore, the limit is 4 over 3. And the last example is limit when x approaches 0 of tangent of x over x. Notice that we don't have sine here. However, we can rewrite tangent as sine of x over cosine of x divided by x. Therefore, we can then write it as limit when x approaches 0 of sine of x over x times cosine, which then can also be rewritten as follow: limit of sine x over x times 1 over cosine x. Now, we have two functions multiplied to each other, right? The first factor, which is sine of x over x, guess what that limit goes to? The answer is 1, because of the theorem. Then for the cosine of x, because when x approaches 0, cosine of x approaches 1, so the second factor also goes to 1. Therefore, the whole limit is equal to 1. As a challenge problem, compute limit when x approaches 0 of cosine of x minus 1 over x. And if you have any question about the challenge problem, please come talk to me. And that is the lesson.